Alright, this is the last video for the NMR spectroscopy slides, and we're starting on slide 42 here. So the topic for this whole video is complex splitting patterns, okay? So what we have here, we're starting with this compound here, okay? So this is allyl bromide. Now, these two protons, they're two protons on the terminal alkene, okay? So what we're going to do in our minds, we're kind of putting our thumb on that proton, and considering how the resulting molecule looks versus covering up that proton there. So if you notice, my thumb, that makes the two remaining protons in a cis orientation. And the proton that's covered up by my finger down here, those two remaining protons are now in the trans orientation. And so if you remember back on the slide that I didn't write anything on, I just had a bunch of different coupling constants. Cis couplings are different than trans couplings. And so so you can just replace with like R or something, and this would be like the Z diastereomer, and this compound would be the E diastereomer. So these two compounds are diastereomers of each other. Stereomers. So when this is the case, the two protons that you can play this game with in your head mentally, that means that they are diastereotopic. These two protons are diastereotopic. Okay, so replacing the cis hydrogen gives the cis diastereomer. And replacing the trans hydrogen gives the trans diastereomer. So the two imaginary products are diastereomers. Okay, so this makes those protons diastereotopic protons. Diastereotopic protons. Diastereotopic protons are capable of splitting each other. So now we don't not only have to worry about this trans coupling, if you will, here, but we have to worry about this proton also coupling to that. And for this proton, we not only have to worry about the cis coupling, but this proton coupling back to that, because these two protons are different protons. And it makes sense because this proton, remember, this orientation right here is locked. So this proton is feeling a different chemical and electronic environment than this one, because this one has some stuff over here, whereas this one only has a proton. So it of course makes sense that they would be non-equivalent, because they're seeing different things. Okay. So here is this NMR spectrum is the spectrum for styrene. Okay, so we'll call this HA, we'll call that HA, and we'll call this HB, and we'll call that HC. Okay, so I'll just colors. I don't know, I'm making this up. Making this up as we go. Okay, so let's do HA. Oh, this is going to get annoying with these colors. HA to HB is, so the coupling for this is 17 hertz. Okay, 17 hertz. So we have HA to HB. And that makes sense. This trans vinylic coupling is a very strong coupling, 17 hertz. Okay. So HA sees HB, and HA also sees HC. HB and HC are diastereotopic protons. So this is a cis orientation, and so the 3-bond coupling for this is around 11 hertz. So this HA sees this HB, so this proton sees one proton. So it splits into a doublet. But then this HA says, oh wait, I see this one too. It's different than this one. So it's split into a doublet because of this proton. And so what happens here is this, what would be a single if it didn't see any protons, it splits into a doublet. But then since it realizes, oh wait, I see another proton too, now each one of these signals has to split into a doublet of their own as well. And so we would call this a double doublet. And here is HA's signal right there, a double doublet. Okay, so our doublet, if this is, say, this is one half of our doublet for H8HB, it has to split again for HC. Okay, and then the other half of our signal also splits in half, so that's why it ends up being a double doublet. Then when we concern ourselves with HB, so HB to HC, so that is a geminal vinyl coupling, right? And that is a 2-bond coupling, right? 1, 2, 2, J, proton to proton, is 1.4 hertz. So HB to HA, if HA is coupling to HB at 17 hertz, HB is coupling to HA at 17 hertz as well. Okay, so this goes both ways. If HA is coupling to HB at 17 hertz, HB is coupling to HA at 17 hertz. So HB is a doublet because it sees HA. But then each one of the signals of the doublet has to split again to HC. So it also goes to a double doublet. So HB's signal will be a double doublet where its large coupling is 17 hertz, and then each one of those signals will split 1.4 hertz apart for the small coupling to HC. And so can you see how this one, the large coupling here, is wider than the large coupling on this one? So you can see that this one is HB. Okay, so HC to HA is 11 hertz, but then HC also sees HB at 1.4 hertz, and so this is HC, and it's this there. So the next slide is just explaining this in a little bit more detail. So since I color-coded this, I didn't do it in my notes, so I'm going to have to pull this off the slide I just threw away. So what we have here is at 6.6 ppm, this is the coupling to JA, or I'll just go ahead and write it down, the 3-bond coupling from HA to HB. So, if you remember, I'll go ahead and pull it back out. 6.6 ppm right here. 6.6 ppm. So this is the one where we had 2 huge couplings, right? The first one, the large one, was 17 hertz. So that splits to 17. So it would have been a doublet right here. Okay? Would have been a doublet. So remember, this is the signal for HA. So this is HA. So A to B is 17 hertz. But then, so this, each one of these signals right here has to split again. So because A also sees C. So this is the 3-bond coupling A to C. The 3-bond coupling A to C. So I'm going to put it up to the camera so you can see that it's 3-bond coupling A to C. And each one of those, if you go remember, was 11 hertz. So this signal had to split apart by 11 hertz. And this one did the same. They both had to split together 11 hertz. Okay. So now we have HB. So if you remember, HB was this one right here, a little bit bigger than 5.5 ppm. Okay, so we still have the 3-bond coupling of A to B, big, strong 17 hertz. So remember, this one was a nice wide coupling here, but then the small coupling was very small. So the small coupling is the 2-bond coupling of B to C. So if you notice, that's a 2-bond coupling of B to C, and that's 1.4 hertz. So what would have been just a doublet, had B only seen A, it would have just been a doublet at 17 hertz. But then each one of those signals had to split in two because it also saw C, and so it's a doublet. Okay. And the example for explaining HC is not on here, but it's the same scenario as HB, except we would have just put in 11 hertz right there, but the small coupling would have still been 1.4 hertz because it's just C back to B. Okay, so the last two slides. So this diastereotopic protons scenario also plays out for positions adjacent to a chiral center. Okay, so if you notice, this carbon right here is a chiral center. It has 1, 2, 3, 4 different things bound to it, okay? And these two protons adjacent to it, these two methylenes, are diastereotopic because of it. Okay, so so what I'm going to do is I'm going to take this molecule, okay, and I'm going to draw the Newman projection of it looking down the C1, C2 axis, okay? So the front, if you will, is going to be this carbon here, and the back is going to be this carbon here. Okay, so Cl is in plane up, and then we have our down to the sides H's here. Okay, so I'll just, for these, what's hanging off C2, I'll just, so there's a chlorine, I'll put it there, there's a hydrogen, I'll put it there, there's a methyl, I'll put it there. Now if you notice something, I'll circle one of them in red, so that would be like that one there, and I'll circle the other one in green, that's that one there. If you notice, they're always, no matter how you spin that around, proton red is always going to feel something different than proton green. Their environments are never going to be the same, and so that's why they are diastereotopic. So here is position 1. All we're doing here, just like how we kind of covered up the two positions, put our thumb on this one, we had a different molecule, then we put our thumb on this one, and we're just doing the exact same thing here. Okay, so if you notice, these two are diastereomers. Position 2 would overlap, but position 1 won't, so they're not mirror images, and they're not the same thing. They are just diastereomers. So these two positions are diastereotopic positions. Okay, so they are diastereotopic. Their imaginary replacements give diastereomers. Diastereotopic protons are usually vicinal to stereocenters, chiral carbons. Okay, so that explains kind of what's going on. And the last slide for NMR spectroscopy, I need to have like a little clapping hands audio playing right now. This is a lot of slides. It's just the NMR spectrum for this compound, okay? So, if you notice, this proton right here is seeing that proton and that proton. So it has a 2-bond coupling and a 3-bond coupling to other protons. Now, if you go back and you look at your coupling constant slide, you would see that non-equivalent geminal alkyl is actually a very strong coupling. When we were doing vinyl, it was a weak coupling, but when it's geminal alkyl, it's a very strong coupling. Okay, so this would be a strong coupling, 10 to 16 hertz, and then the 3-bond coupling would be around, somewhere in the 7-8 hertz range. Okay, and so those 2 colors I did. I think it was these 2. So same thing for this proton. It's seeing that proton in a 2-bond coupling, and it's seeing that proton in a 3-bond coupling. Okay, now this signal here is seeing, I guess I just did it like it's seeing those 3, that one, and that one, and it is splitting them into a 1, 2, 3, 4, 5, 6. It's splitting into a hextet or a sextet. Interestingly enough, so the absorptions for the methylene protons on C1, distinct absorptions for the methylene protons. These hydrogens are diastereotopic and are chemically non-equivalent. Okay, so that's it for, I guess I could have, the methyl is these 3 only see 1 proton, and so they're a doublet. I guess I could have done that too. That's all of these slides for NMR spectroscopy. All right.